Hello everyone, my name is Andriy Vlazenko. I am a senior data scientist with 19 years of experience in climate research spanning various projects, including my PhD at University of Heidelberg. Over the past 7 years, my work has focused on developing AI tools, particularly for recovering lost time series, building forecast neural networks, and more. Some of these methods stem directly from my professional research and have been published in scientific journals, while the others are just passion projects. You can explore more of my work, including open source and detailed explanation of my code, in my GitHub page. Let's dive into these methods now. Here is an outline what I'm going to talk about today. So, first topic is, can a neural network be more efficient than complex scientific software? Next one is, can a neural network fool an AI spotter and generate a human written text? Can generative adversarial neural networks be simple and efficient enough for teaching? And can we extend it for generating a real looking images? And the final topic is big data restoration denoising algorithm PEFRA. So let's meet chemistry estimating recurrent neural network CERN. Why CERN? Air quality directly impacts our health and longevity, making it a critical issue for all of us. CERN is a simple but powerful neural network designed to predict air quality changes across Europe, providing valuable insights for researchers, policymakers, and communities. Its accuracy on the same level as complex numerical programs that require thousands of computational hours on a supercomputer. Compare CERN estimated and true NO2 anomalies, so they almost coincide. As I already told you, this scientific software requires thousands of hours of calculations on a supercomputer. Here it is on the left. However, CERN is at least 700 times faster than these programs, and it can run on a simple laptop. I think you can compare the costs. If you want to read more on this, so you can find my publication here. Can a neural network fool an AI spotter generated human written text? So here is a story of a storyteller. Picture a teacher asking an unprepared student who isn't particularly studious but highly inventive to answer. Gives fantastically creative but typically wrong answers, entertaining the whole class. This neural network is a kind of such student. It generates similar rhythmical answers just for entertainment. Start a sentence and watch how it spins up in an amusing narrative as long as you like. Here is an example how I do this. So I put some text here. Then I put some how many words I want to see in the generated text. And now it generates me the text. Note, so actually it says so that the crossbow of the Roman Empire was brought by Chinese. So far this is wrong. So maybe in the nearest future we'll get some findings in the archaeology, but it is wrong. But for the person who is not familiar with the history, so this answer will sound quite smart. And that's what the storyteller is about. Here are some other samples of generated text. You can find more of them on my GitHub page. Note that Grammarly and ChatGPT based AI Spotter give 80% probability that this text is a human written. This is another my hobby topic, so this is short and fast generative adversarial neural networks, ShortGAN and FatGAN. ShortGAN is a simple teaching aid that I have created. It generates missed handwritten numbers from a noise after 100 epochs of training on a simple laptop equipped with a CPU within several minutes. The FatGAN is an advanced version of the ShortGAN. Its architecture allows training such a neural network on a single GPU and produce from noise colored images of cats, humans, etc. just in a couple of days. Below is an example of such images obtained in the middle of the training. Also, the training is far from finished, and you already can see some reasonably looking figures. Physics-enabled fluid flow restoration algorithm is the final topic for today. This algorithm was especially designed for particle image velocimetry (PIV). PIV is a technique for determining the velocity of a fluid by evaluating the motion of a special luminous particle seated in it. Figure on the left shows an example of PIV experiment where particles overflow the airfoil. However, PIV requires ideal laboratory conditions, which is impossible to achieve when measuring currents in the core store. Turbid seawater leads to high noise and data losses. My PEFRA algorithm can efficiently recover the lost data. Here is an example. The rare red arrows denote the noisy input from the PIV. The black arrows are the recovered fluid velocity field. See how PEFRA did a remarkable job. Find more about this algorithm in the corresponding scientific publication that I have it with my co-authors. So, thank you very much for listening. That's all for today, and visit please my GitHub page. Bye bye.